But we're going to talk a little bit about strong and weak acids today. And this kind of will directly apply to tomorrow as well. We're going to talk about strong and weak bases tomorrow. So this is the same kind of deal here, guys. So we need to pay attention here. Strong and weak acids. Some acids of similar concentration show more acidic properties than others, of course, because some are stronger acids than others. A stronger acid reacts more quickly with active metals like zinc and magnesium, has a lower pH, of course, because there is more H3O plus, and more hydronium ions, has a greater electrical conductivity because, of course, there's more free ions to conduct electrical current. Some of the stronger acids, of course, do this very well, and the weak acids, well, different degrees, but not as well, of course. All right. Strong acids completely ionize in water. We've talked about this before, all right, quite substantially here. We know that strong acids, for example, completely ionize in water. So what does that mean? If you took 1 molar HCl, and this is what we did, yesterday with a little bit of a pH and pOH stuff. If I took 1 molar of HCl and I put it into water, I would expect to get, okay, 1 molar of H3O plus ions and 1 more molar of chloride ions, and both of those, of course, are applicable and important for us today here. So that's what I would expect to get. Yes? Okay. This is prior to ionization, and basically after ionization is complete. You guys, everyone's okay with that? Everyone understands that? Yes? No? Okay. Strong acids completely break up when you put them into water. For a list of the six strong acids, because there is 6 of them, I made you memorize these in Chem 20. I don't make you memorize them anymore. They're in your data booklet, and they're the top 6 there above that, basically that kind of bolded line there. So if you look in your data booklet here, guys, they're the top 6 that you see at the top here. For example, perchloric, hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric are the 6 strong acids. For any of those 6 strong acids, this is exactly what happens. They're all the same. Okay? They break up 100%. So if you put 1 molar in of hydrobromic acid, you're going to get 1 molar of hydronium ions. And if that's the case, remember, if we're looking for, today our job is going to be to figure out the concentration of the hydronium ion. So I want to know the concentration of this right here today. And of course, because once I know the concentration, the next thing I can do with that is figure out the pH of this particular acid here. And by the way, if I was going to do the pH of this, I could do this quite easily because I already have the concentration here. I take negative log of 1, and I would get 0 for a pH for this particular acid. Done. Okay? All strong acids behave like that. Yes? You guys know that, correct? This is review. Yes? Okay. So that's easy. Those are easy ones because the strong acids completely break up. They completely ionize, 100%. All right? Now, by the way, I guess maybe I did this last class and then I thought maybe I shouldn't, but maybe I'll do it again. If I was going to do the equilibrium constant for this, look, equilibrium constants means at equilibrium, yes? At equilibrium. So if you think about this, guys, I'm not going to use Kc for this one because today you're going to learn about something called Ka, which is the equilibrium constant for acid. That's the only difference, so it's a little different abbreviation, that's all. Same stuff as we did before. I'm going to call this Ka here. And I would say Ka is what? H3O plus over Cl minus over HCl in this case, right? We don't include water because water is a liquid, and we don't include, what else don't we include? Solids, right? So we don't include that in the Ka expression, or the Kc expression is what we did the other day, or the Kw for that matter, okay? Look, what happens when I put this in? I put in 1 molar for this here. I put in 1 molar for that, and I put that all over 1 molar. What do I get as a Ka value? Ka value turns out to be 1. Okay? And what you're going to learn here is that Ka1, really Ka is a percentage that's been converted to a decimal. So, for example, what this means is that basically 100%, for every 1, you get 1. Okay? So that's what Ka values are. They're a percentage that have been converted to a decimal. All right? This is the decimal form. What was the percentage that goes with 1? If I change this back to a percentage, isn't this 100%? Yes? If I change 100% into a decimal number, it's 1, yes? That's what Ka values are, all right? And that's what we're going to talk about today once we get there. So basically, they're saying that this breaks up 100%, or more even perhaps. Or basically what they're saying is if it's very, very large is what they say here along your thing here, which we'll talk about in a second, okay? Now, weak acid's only partially ionized. So what we just did with that strong acid, we can no longer do with a weak acid because we don't have 100% ionization. If you look at 1 molar acetic acid, okay, this is actually what happens with 1 molar acetic acid. If I took 1 mole of acetic acid, which is a weak acid, by the way, okay, weak acid, and if I put it into water, you'll notice, first of all, first things first, it's a double arrow. Means it's in equilibrium, goes back and forth. For every 1 molar here, I get 0.00424 molar here, just so you can kind of see the decimal number, what that number actually is, because I know sometimes it's confusing with scientific notation, okay? And you get 0.00424 molar here, 1, 2, 3, okay? Yeah. Well, yes, but we're putting it into water. That's the concentration we're going to start with. Okay. So now 1 molar. Okay. Maybe it was diluted, kind of thing, because most acetic acid usually comes stronger. So maybe it was already diluted to 1 molar. So putting it into water. 0.00424. So you can see right away that when I start with 1 molar here, I end up with 0.00424 molar there. Okay, that's not a 1-to-1 relationship. That's not ionization of 100%. In fact, pretty opposite. If you started with 1 here, 1 molar, another way to think about this, if you start with 100 molar acetic acid, to be silly, okay, 100 molar, that would give you 0.424 molar here. That means it's 0.424% ionized. That's it. Okay, out of every 100 moles, you get 0.424. That's 0.424 out of 100, or 0.424%. Okay, that's not lots. Yes, pretty small. So how do I know this? And that's what we're going to talk about today. How do I figure that out? Because obviously I gave you the fact that it was 0.00424. How do I figure that out? Well, that's what we're going to do today, okay, with weak acids here. But you can see that it's not 100% ionized, of course. But hey, look, can I still figure, now that I know this concentration here, by the way, let me just get rid of this because that's kind of silly, but now that I know that concentration, could I figure out the pH of this particular one? Sure. I would take, once again, pH is the negative log of 0.00424. And actually, it's done for you on the next page here somewhere, or somewhere along the way there. But that works out to be, I believe, 2 point something. Is it what? Sorry? 2.373. Okay? So you can see, in fact, that the pH is 2.373. For that one, that's a weak acid, and I get a pH of 2.373. I started with 1 molar of it. And I started with 1 molar of hydrochloric acid, which is a strong acid, and I got a pH of 0. Okay? By the way, remember, every pH step that you go is a factor of 10. So basically, I started with a 1 molar here, and it's 2.3. I started with 1 molar here, and I got 0. So that's about 100 times weaker. Okay? Roughly. All right? So we can see that we probably have a little bit more work to do with the weak acid, because what I need to figure out is how much is it actually going to break up, all right? And that's what we're going to talk about today. So like all strong acids, HCl ionizes 100%. Acetic acid, only about 0.424%. Very little breaks up. All right? So, if I calculate both of those pHs, that's the comparison we would have there between those two. Okay? 0 to 2.373. So, now we're going to talk about the acid ionization constant. You will find these constants in your data booklet. Along the far right-hand side here, you will see Ka values for these acids. All right? Now, if you look at the these 6 strong acids, you'll just see it says very large because you don't need to worry about a Ka value for that because it breaks up 100%. So basically, you know that it's going to break up 100%. You don't even need to worry about doing this, and we'll talk about that coming up here. However, starting at the hydronium ion, you see that's a 1 there. And then from there, we have oxalic acid, sulfuric acid. And you'll notice that as you start to go down this table, I'm looking in the left-hand column with all these acids here. If you look at the Ka values, you'll notice that the Ka values start to get smaller and smaller as you go down this table. Okay? Because you're starting at basically 1, and then 5.6 times 10 to the negative 2, 1.4 times 10 to the negative 2, all the way down to 1 times 10 to the negative 14. Okay? That's a pretty small number. So the Ka value starts to get lower and lower, basically smaller and smaller, as you go down the table. So what this means to you is the following. As the Ka value goes down, less basically ionizes, right? Because Ka measures the percentage of ionization. So as you start to go down, the acids become weaker and weaker. Because the 6 strong ones are here, and then oxalic acid is probably the strongest of the weak acids. And then we start to go down, and the Ka values get smaller and smaller, which means they break up less and less and less and less. Remember, Ka is the percentage that's been turned into the number so that you can actually use it. Okay, so we don't have to change it, from 99% to 0.99, for example. That's what Ka values done. They've already put it into decimal form for you. Okay, so as you start to go down and down and down here, they get weaker and weaker. Okay, this table looks, by the way, is going to be very similar to another table we did, which looks like this one here, electrochemistry. Yes, SOA, SRA, remember that? Strongest oxidizing agent, work your way down. Strongest reducing agent, work your way up. Yes, same thing here, guys. Okay, that's why this table is basically the same thing. Strongest acid going down. Guess what? For every acid, there is a conjugate base, we say, and then we're going to talk about that tomorrow. So for all the acids that we go down here, the strongest base is in the bottom right, and we're going to work our way up to the weakest base. Because if the acid is very strong, the conjugate base has to mean basically the base is very weak, and vice versa. If the base is very strong, the acid that goes with it has to be pretty weak. Okay? They have to go in conjunction with each other. All right? So all acids ionize to some extent in water. Some better than others, yes. Strong, very good. The one probably at the bottom here, probably not very good at all. Okay? But it does still ionize to some extent. We're going to use Ka values, can be used to determine the extent of the ionization, basically the percentage that it breaks up. The larger the Ka acid is, the stronger it is. That's something important to know, by the way, because we're going to ask you to compare acids at some point in time, probably. Which one's stronger out of the weak ones. All right? Next. The complete ionization of strong acid is a quantitative process. That basically means it's a one-to-one relationship. It's very quick and easy to do. It's directly, everything here turns directly into everything on the product side. Done. Okay? Strong acids have a very large Ka value, so that basically means that probably a number bigger than 1 or whatever the case might be. And an ionization of a strong acid would look something like this. This is a pretty common general formula that you guys should probably know. So whatever that acid happens to be, H+, and this A- part here, the H+ will attach itself to the water, of course, to give you H3O+, and the anion left over. Okay? It's a pretty general way to write acids, HA. Okay? A stands for basically the anion or acid that we're talking about here. All right? So pretty common, typical, general type of question. Any HA, and this is the ionization of any strong acid, of course. Notice it's quantitative, which means it directly breaks up here. So quantitative, look, single arrow means that all of this turns into all of this stuff there. Okay? Single arrow. These are easy to do because whatever the concentration is here for HA, concentration of H3O plus is the same. Negative log, done. Found the pH. Okay? Here's what the ionization of a weak acid looks like. Same thing. HA and water gives you some of this and some of this, but notice double arrow because now it has to reach equilibrium. Okay? And if we were writing out the Ka constant here, the equilibrium constant at equilibrium, we would say this. Products over the reactants. Products, right? Products over the reactants. We leave out water. Okay? So products over the reactants at equilibrium. All right? So, next. The Ka value can be used to calculate the H3O plus concentration, and if you know the H3O plus concentration, you therefore can find the pH of a weak acid. All right, so here's our first example, and this is where it gets a little dicey, if you want. Okay. Now, I think there was something else I wanted to tell you guys, but I actually kind of forgot here. So, what else did I need to tell you? Yeah, I don't know. Let's go ahead and do this. So I'm going to show you two ways to do this question. Okay, and I need to show you these two ways because I need you to understand what is happening here. All right, this is important. So you might say, well, why did you show me the first one? Because you have to understand the process that's involved here. Okay, and yes, it can get kind of complex. Okay, but it's not a big deal. Okay, this is something that you guys should be able to do. You guys are math 30 kids, so we'll figure it out. We got a 1 molar of what? HCN. So I'm going to start with good old-fashioned equation here. And water. And the first thing I should ask myself is HCN a strong acid or a weak acid? Because if it's a strong acid, we got a pretty easy question here. Is it strong? No. So once again, I'm going to use double arrows then to represent that this is not going to completely ionize. And I'm actually going to get this here. Okay? And, you know, this is kind of stoichiometry stuff, but we're going to start with a 1 molar solution here. Okay? You can pretend whatever. If you want to pretend we got a liter of this, that's fine, or 2 liters or 4, or I don't care, whatever. It's all going to take place in the same amount of water, so it doesn't really matter. But I have a 1 molar. I'm going to start with 1 molar. Now, what you have to understand is I'm starting with 1 molar of HCN. Starting with it. And then I'm going to put it into some water, let's say a liter or something. I don't care, whatever you want to pick. How much H3O plus do I have before I start putting it into water? Initially, I have 0. So, we're going to build a little ice table here. And we're not even going to talk about ice baby, because that we don't, trust me, you don't want to talk about ice baby today, okay? Because you're going to be like, oh, ice, no baby, okay? No ice baby. So we start with that. That's before it ionizes, okay? Here's my 1 molar acid. Now, here's my 1 molar. I'm going to put it into some water, let's say a liter. So now I dump it into water, okay? That is the change that's taking place. Now, how much does it go down by or up by? In other words, you know, what's my final equilibrium concentration? Because this is what we did before with ice tables, and the answer is I have no clue. That's what I'm trying to find. What is the concentration at equilibrium is what I'm trying to find. I have no idea what this is, okay? And it's going to be different for each one. So I'm starting with 1 molar. If I had 2 molar, it'd be different. So I have no idea. But I do know this. Do you agree that if this goes down by, well, first of all, if if I start with 1 molar and I got 0 there, which way is this equilibrium going to shift until it reaches equilibrium? To the right, correct? So if I want to shift it to the right, in other words, to get to equilibrium, I have to use up something of HCN, yes? So I'm going to put down, what is that something? Don't know. So I'm going to say X. I'm going to use up something. Something's going to get used up there. And if I use up X here, how much do I make over here? Plus X, right? Because whatever I take out of this 1 is how much I'm going to make there. And likewise, don't forget, this is a 1-to-1, so I also have to increase this by X too, don't forget. Okay? Because that also goes up by X, because for every one of those, remember, I'm making X and X over there. All right? So, what's the equilibrium then? What happens at equilibrium? Well, once again, I don't know what X is. I wish I did, but I don't. If I did, if I did know what X is, would I be continuing to do this question? No, because I'd know H3O+, right? And if I knew H3O+, could I find the pH? Sure. So that's the purpose of this. I need to figure out what is H3O+, what is X, so I can figure out the concentration for X, H3O+, and then I can take the pH of that. But I don't know X, so I need to find that out. Do you agree that this would be 1 minus X? Whatever that happens to be, yes? So whatever that I took away there, that's going to be 1 minus X at equilibrium. This is going to be 0, and then I added X, so that's going to be X, and that's 0 minus 0 plus X, so that's X there. That's at equilibrium now. Only now should I be talking about Ka values, because Ka values are for at equilibrium, like everything we've done so far. Whether you think or not, when you write down Kc, that's at equilibrium. I don't care about the initial, I don't care about the change, I care about equilibrium. That's the whole unit, guys, at equilibrium. So that's at equilibrium now. Now I could write down the Ka is the H3O+, and in this case the Cn minus, all over the HCN. Right? And then I'd say to myself, what could I possibly put in here? Do I know a Ka value for HCN? And the answer is yes, it's in your data booklet. So you look up HCN, hydrocyanic acid, is what that's called. And it's quite far down, by the way. It's 6.2 times 10 to the negative 10. Basically means it ionizes 6.2 times 10 to the negative 8%. Pretty small. That's 1. Okay. What's H3O+? Well, that's an X. What's Cn minus? What's HCN? Well, I actually know that one. It's 1 minus, well, X. So those are the concentrations that I've determined at equilibrium. So we need to solve for X. I will maybe do a little cross multiplication if that's okay for you. 1 times X squared equals 6.2 times 10 to the negative 10 times 1. 6.2 times 10 times 1 is 6.2 times 10 to the negative 10. Right? Don't forget, this is what we call that binomial in math, yeah? Property, right? Twice. 6.2 times 10 to the negative 10 times 1. 6.2 times 10 to the negative 10 times negative X. So that's a negative 6.2 times 10 and negative 10 times X. Okay? Does this look like, I've talked about this before probably, but who recognizes that? X squared, X number, quadratic formula, yes? Yes. So you can type this in your calculator, probably you could do a graph, you could find the roots, etc., etc. I've done it for you right here. X squared, let's take this to the other side here, so let's plus 6.2 times 10 to the negative 10 X. We'll take this to the other side, minus 6.2 times 10 to the negative 10. That all equals 0. So that is ax squared plus bx plus c, yes, correct. Look familiar? Sure. There's a formula for it, quadratic formula. X equals negative b plus or minus square root of b squared minus, or b squared minus 4ac, blah, 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 equals 2a, yeah. Calculator, you guys probably use calculator stuff. There's a program sometimes you can download that does that for you, etc., etc. I typed it in, I did a Google search on it, because Google has everything apparently, including YouTube videos that you guys missed when you guys were away, so you should look those. Including a quadratic formula. And I plugged it in there, and you know what the answer I got for this was? Well, you get two answers, by the way, obviously, right? Because, remember, the plus or minus gives you two answers, right? Negative b plus or minus, etc., etc. One's negative, that doesn't make sense. The other one's that one right there. 0.000248991979. Is the answer to yes. That is X. That is the concentration of the hydronium ion. Pretty small, is it not? Makes sense because what did I say? It ionizes about 6.2 times 10 to the negative 8%, which is the Ka value of 6.2 times 10 to the negative 10. Pretty small. So I can say here, hydronium ion concentration is 0.00048994.072. And if I want it to be silly, I could say, you know, that's being silly. If I wanted to actually round it to significant digits, you look back to the question, 1.0 molar, so therefore I would say probably 0.0025 moles per liter round. Zeros in the front don't count digits, right? And I did that for a reason. I wanted to show how small that number actually is. I think sometimes we lose perspective when we write scientific notation. That's 5 times negative 5. Yeah, or no, 5. 1, 2, 3, 5. Right? So sometimes we lose perspective. So for 1 mole of HCN, I'd expect to get 0.005 moles. Can I figure out the pH now? Yep. pH is the negative log of 0.0000248, etc. And when I take the pH of that, you'll see. Okay. So negative log of 0.0000. I'm actually going to type in as many numbers as I can here. 299489197.072. 4.603. Okay. You know what? And I'm going to be a little bit here. I'm just going to write that number down here. Significant digits wise, we would have to go with 2, right? Because 1.0 was the original question, and 2 after the decimal, so 4.6. Okay, good. Alright, that's not bad. Now, think about this though. What would happen? Back up to here. I'm gonna. So 4.60 is your answer. Yeah, that's your pH. And this is the concentration. Look at this here for a second. Go back up. I'm going to use this number right here. That's the number there. So let's go back up here. Remember, I found X. So that's this number right here. 0.00025. 0.00025. That's there. How much does the concentration go down to equilibrium? 0.00025. Right? 0.00005. What is 1 minus 0.00005? Pretty small, isn't it? Actually works out here 0.999975. Okay? Is 0.999975 much different than 1? No, it's pretty much the same, is it not? So the question is, you know, could I maybe just pretend if this is 1 molar here, and since I lose so little, I lose 0.000025, is that going to make a big difference in the big scheme of this stuff? Because if it doesn't, let me tell you, this becomes a pretty quick question. We don't have to worry about quadratic equations anymore. Because if I assume that this is 1 mole here per liter, and then I assume that this is just 1 here, and I forget about the x, in other words, I forget about that little bit that I lose, that is obviously going to be gained here. Yes, I realize that. But if I forget about that little bit that I lose, do I have 1 minus x anymore? I have down here 1, right? Do I have to do the quadratic formula anymore? Nope. So, when can I do that? When can I assume that I don't have to use the quadratic formula? In other words, how would this differ if I pretended at equilibrium it was still a concentration of 1 mole per liter? I will show you, because this is what you guys are now going to do after you copied all that down. I have to explain that to you because you have to understand that yes, I lose a little bit, okay? If that changes a little bit, I have to lose it. However, it's not substantial. Are you going to have to worry about that? And the answer is possibly yes. So you have to understand it starts at initial. I am going to lose a little bit, and I get to equilibrium. Would it affect a question like this? Let's take a look and find out. If I was going to do this question over again, I'd say this. Maybe, and you do want to write this down, please. Okay, I'm going to assume that this is 1 molar here. This is the same one still. I'm going to do it over again. I'm going to show you how to do this with the approximation. This is the second time of the same one. Okay, if I assume that this is 1 molar here, okay, and that would be my initial, I'm also going to assume at equilibrium this is still 1 molar. I started with 0 and 0, and I still know that it's going to go up by x and up by x. But what I've taken out here is this minus x part here. So I know that that little part that I've lost is so small, I'm going to forget about it. Okay? I'm going to assume it's still 1 molar per liter, although we just proved that it was actually 0.999975. Okay? I'm just going to say, you know what, that's 1. It's close enough. Forget it. Okay? Get over it. And then I'm going to do my Ka thing here. And I'm going to say x times x over 1 here. Okay? I'm going to put in my Ka value, which of course is 6.2 times 10 to the negative 10, which is x squared over 1. I'm going to solve for x squared, so x squared is going to be 6.2 times 10 to the negative 10 times 1, yes? So x squared is going to be, or sorry, x is going to be what? So I'm still solving for the hydronium ion. What I did was I said, instead of pretending it's, instead of doing that little bit of difference, I'm just going to pretend it's 1. I'm not going to worry about the minus little bit that I lost. If I take the square root of 6.2 times 10 to the negative 10, here's the number you get. I'm going to do this in this point here, 0.00248997992, basically, and that's as much as my calculator will do for me. That's the concentration of hydronium that I get. So, check this out. 248997922. Here was the other number here. This is from the last page. 0.0002489948919799072. Look, all the way same up to there, yes? How much different is that? Well, don't forget, you're talking about, you're not even just talking about this, you're talking about all these zeros in front, right? So not until the 1, 2, 3, 4, 5, 6, 7, 8, 9, not until the 10th decimal place, right, does it actually change. And if I take negative log of those two numbers, once again, I'll take negative log of this one, which is still my calculator, by the way, watch this, negative log. Here's what I get for the negative log for this one here. It was 4.603804155. And on the other sheet here, what was it again? Is that way at the top here? 4.603809562. 3809. And there's 3804. Okay? Are you going to have to ever worry about 1, 2, 3, 4, 5, 6 decimal place in a pH? No, probably not. Okay? So, does it matter which way we use? Nope. Which way should you use? The easier one, because you don't have time to worry about quadratic formulas. I told you, so you understand that it starts with I, C, and E. That's actually what's happening. So listen, you don't need to use the quadratic formula with one exception. And this has to hold true. And that exception is right here. If the HA concentration, so if the acid concentration is 1,000 times larger than the Ka value, you can use the approximation. In other words, you can get rid of that minus X part. Okay? The question is, for us, right, look, our concentration of HCN was 1 molar. Our Ka value for HCN is 6.2 times 10 to the negative 10. That's what we're comparing. The concentration of the acid I give you in the question compared to the Ka value. Is 1 molar 1,000 times bigger than 6.2 times 10 to the negative 10? Oh yeah, it's quite a bit bigger, is it not? Like 10 to the 10 almost, yes? Roughly, give or take a little bit. 10 to the 9 maybe for sure. That's a little bit bigger than 1,000 times, yes? So we can use that approximation. I just proved to you that it works to the 13th decimal place or whatever it was, something stupid like that. Okay? But you do have to keep that in mind, because if it's not, and you might say, does that ever happen where it's not? Oh, it could. Yeah. Then you have to use the quadratic formula. Okay? Will you ever be asked that on a diploma? No. Will you have to understand the ICE table that it starts out with? Yes, absolutely. And I have some questions for you based on that today. Let's look at the next one here today. This one here is calculate the H3O plus and the pH of 1 molar HOCl, hypochlorous acid. Same thing, guys. You'll notice that these start to follow a pattern, HOCl and water. Weak acid, so I know double arrow, H3O plus and OCl minus, hypochlorite. Okay, I know that I have a 1 molar solution here. That's my initial concentration. I'm going to assume, well actually maybe I shouldn't, is 1 molar bigger than the Ka value by 1,000 times? That's the question. And the Ka value for this one is what? 4 times 10 to the negative 8? So is that 1,000 times bigger? Oh yeah. If you're not sure, just type it in your calculator. Take 1 divided by 4 times 10 to the negative 8. It's 1,000 times bigger, I guarantee. So that's probably a good assumption. So initially, that's the concentration, and I would have 0 and 0 here. At equilibrium, I'm going to assume I have still 1 molar, although that's a lie, because it has gone down a little, and I'm not sure how much I have there. Okay? How much do I have there? Well, that depends on the Ka value, how much it breaks up, right? So, X, let me write it out here just for a little practice for me. H3O plus, hypochlorite, all over HOCl, hypochlorous acid. Okay? So, Ka value for this one I think was 4 times 10 to the negative 8. This here is X, this is X, and this was 1 molar. Okay? Is 4 times 10 to the negative 8, is that right? I'm just going kind of based on memory here, which is not great. Cross multiply and solve. 4 times 10 to the negative 8 times 1. So it's not always going to be that, by the way. And X squared. what does x turn out to be? I think it's 2 times 10 to the negative 4. Does that sound right? So now, what have I done? I've found the H3O plus concentration. Yay for me. So H3O plus concentration is 2 times 10 to the negative 4 moles per liter. The pH of this would, of course, be the negative log of 2 times 10 to the negative 4. And if you do that, you get 3.69897. Don't forget significant digits. Okay, I didn't really do a good job of that today just because I wanted to show you the differences. You know, when it really comes down to it, it's not a lot of difference. Significant digits, remember you had 1.0 in the initial question, so that's 2 in the concentration, which means 2 after the decimal. So I got to round it to 0.70 in this case, 3.70. Okay? So that obviously works a lot better, a lot easier. Okay? But we have to keep that in mind that that's really what's taking place here, right? At equilibrium, that HOCl acid is not 1 molar. It's a little bit less. It's about, okay, well, it's about 2.0 times 10 to the negative 4 less, roughly, okay, roughly. So just keep that in mind. You're going to get questions that say something like this, okay? Could you work backwards? So could we work backwards in this case? If I gave you all the equilibrium stuff, could I find out the original constant? Could I figure out HOCl at equilibrium if I gave you the pH of this? If I give you the pH, can you find the concentration of this? Can you find the concentration of this? They have to be the same, yes? So now you know this and you know this. Could you find with Ka, if I know this and I know Ka, could you find this? Sure. Then, that's at equilibrium. Then my next question would be, what happened before equilibrium? In other words, how much did it decreased by a certain amount to get to equilibrium? What was the original concentration to start with? Okay, so why do I show you the first one? So that you understand you're not starting at equilibrium. You're starting with 1 mole per liter with nothing. Then it goes through equilibrium, you get to equilibrium. Great. Now you can calculate H3O plus. But you don't start at equilibrium, unless it tells you the equilibrium, which it's probably not going to. Okay? So just keep that in mind when you're looking at these questions here. Some are going to be pretty straightforward. Some are going to be, hey, if it's a strong acid, do you got to worry about all this? No. Done. Right? Easy. So make sure, because the worksheet I gave you today is called strong and weak acids. So strong acids probably may be on there. So keep that in mind. Don't go through all the work if you don't have to. This is only for weak acids because we don't know how much it ionizes. That's what the Ka value tells you. That's the data booklet. Okay?